In Bayesian analysis, we don't just estimate parameters, we can also account for uncertainty in model selection. Often we're faced with multiple competing models, each with different sets of predictors, and we need to decide which one is best. In traditional regression, we might use model selection techniques like AIC, BIC, or cross-validation to pick a single best model, but Bayesian statistics offers a more elegant approach, Bayesian model averaging, BMA. Instead of choosing just one model, BMA averages over multiple models, weighting them based on their posterior probability. This means that instead of committing to a single model, we incorporate model uncertainty into our predictions. This is especially useful when we're unsure about which variables should be included in the model or when different models produce similar levels of accuracy. Think of it like forecasting the weather. Instead of relying on a single weather model, meteorologists look at multiple models and average their predictions, weighting them based on how reliable they've been in the past. Bayesian model averaging does the same thing for statistical modeling. It combines predictions from multiple models, taking into account their relative likelihoods. Mathematically, BMA is based on Bayes' theorem, but applied to models rather than just parameters. Each model MIM-I has a posterior probability given by the probability of model MIM. I given the data is proportional to the probability of the data given the model, multiplied by the prior probability of the model. This means that models that explain the data well and have reasonable priors will receive higher weights in the final average, while weaker models will contribute less to the final prediction. One of the biggest advantages of BMA is that it reduces overfitting by spreading uncertainty across multiple models. Instead of relying on a single, potentially overconfident model, BMA ensures that predictions incorporate all plausible explanations for the data. This makes it particularly useful in cases where the true underlying model is unknown or when there are many competing explanations. BMA is commonly used in applications such as economics, where multiple models might explain market trends, ecology, where different environmental factors interact in complex ways, genetics, where various genes might contribute to a trait, but we're uncertain about which ones are most important. However, BMA comes with some challenges. The computational cost can be high, especially when there are a large number of possible models. Running MCMC methods for multiple models requires significant processing power, and if the number of models grows too large, it can become infeasible. Additionally, choosing the prior over models can be tricky. If we assign equal priors to all models, we might overrepresent complex models simply because there are more of them. Despite these challenges, Bayesian model averaging provides a powerful way to quantify model uncertainty, making it one of the most flexible tools in Bayesian statistics. Instead of treating model selection as a separate step, it integrates model uncertainty directly into the inference process.